know how to solve systems of quadratic and linear equations using substitution as well as graphing. We're going to talk about how to take real world situations, word problems, and create these systems on our own prior to solving. So when we're dealing with what we know are quadratic and linear systems, we're looking in the problem for two things. We're looking for something that's moving in the shape of a parabola in order to generate our quadratic equation. And then we're looking for something that's moving in a straight line, which is going to represent our linear equation. So all of these systems are going to be created using moving objects from real life scenarios. So in our quadratic function, as we're creating the equation, we're going to run into one of two things. Either it's going to give us the equation for our parabola. It might include some variables that we have to decipher. It might just give us the full equation. But either way, it'll either give us that equation or it'll tell us 3 points or 3 different places that this parabola is going to pass through. And we're going to have to use those to create our own equation using a regression. So either it'll give us the skeleton of the problem and we'll have to find the values to plug in, or it will give us those 3 points and we will use a regression in order to find the equation. So once again, these regression instructions right here are going to be for those of you that have a TI-84. So the video previously was how to do it on Desmos. So if you have a TI-84, these instructions could help you use that to do your quadratic regression. If you need more help, of course, I can give you more assistance on that. But we're going to focus on Desmos in our example since that's what everyone has use of. Okay, so this is for our parabola, or usually in our real life scenarios, or most of the time we see it like this because it is an object that follows the parabolic path. Okay, our linear equation is going to represent our straight line. As we know good and well, in linear equations, we have to fill in 2 values. We have to fill in the slope, we have to fill in the y-intercept. So the slope is going to represent the rate of change or the speed of the object that's moving. And then the B is going to be our starting point. So you'll see in the notes here that it says that that typically is going to represent the initial height of something that's moving in a line. Okay, so I want to actually look at example 2 first because this is a really good example of physics. So it says it's a projectile motion problem. And this is one where it gives us the skeleton of our parabola. And we're going to have to fill in. It gives us our A coefficient of -16. We need our B value and our C value. So it says a puncher kicks a football. Its height at the point of contacting his foot is 2.6 feet. The ball will travel at a rate of 59.8 feet per second. A blocker's hands are approaching the ball at a rate of 4.7 feet per second. His reach started at 6.6 feet. Okay, so from that scenario, we're supposed to get a quadratic equation and a linear equation. Okay, so you can see here that the football is the one that's going to follow the parabola. So we know that this quadratic equation right here is going to represent the punter. It's going to represent the kicker. Okay, the height at the point of contacting his foot is 2.6 feet. So right here where it touched his foot, that's the starting point of 2.6 feet. So if you recall, when we did attributes, this C value represented also our y-intercept or our starting value. Okay, if we come up here, it also tells you that h sub 0 is our starting height, and then v sub 0 is our starting velocity. So you can think of that h sub 0 as the original height. That O can stand for original. And then v sub 0 is your initial velocity, your original velocity. Okay, so our initial height is 2.6, and it says that it's going to travel at a rate of 59.8 feet per second. So right here we have 59.8. So we have h of x, or the height of the football, is -16t squared plus 59.8t plus 2.6. Notice that 0 on my variables does not move along to our final equation. V sub 0 and H sub 0 are just the names of those placeholders or of those variables. Okay, so this all represented the punter. Actually, I could have included that too. Okay, we're going to do our linear equation in blue. So this right here is the blocker's hand. So he's starting right here, and he's trying to block the football. They're trying to intersect right here. So it says the blocker's hands are approaching the ball at a rate of 4.7 feet per second. His reach started at 6.6 feet. So we know that y equals mx plus b. Okay, we can tell that our starting point right here is 6.6 feet because it says started. So we're going to start at 6.6 feet. And then his hands are traveling at 4.7 feet per second. So if he's starting at 6.6 feet, he's going to jump to try to reach that ball. He's moving upward at 6.6 feet per second. Sorry, not 6.6, 4.7 feet per second. Okay, so that's going to be our slope. So we have y equals 4.7 x. Okay, so here are our two equations. Okay, another name for h of x, remember h is just the name of this particular function. We can also call this y so that we can type it into decimals. I've already got both of our equations typed in, and as you can see, we do intersect in this system. We actually have two intersections. So something we want to remember when we're dealing with real world situations, we're only working in quadrant number 1 of our coordinate plane because we can't deal with negative seconds and negative height of this football. So we're only looking at the positive x and y values for this scenario. So I'm going to actually look at both intersections. Okay, so right here, we've got one intersection, and then up here, we've got another. So both of these happen to be positive values. So if you think about it, we're going to look at the very first time that they intersect, because as that football is going up, once the blocker touches the football, it's no longer going to continue to move on this red parabola that we have graphed, because that blocker's hand is going to knock it off of the parabola. So if this first intersection were to be at a negative value, we would know that as part of the parabola, that does not apply to this problem. But since we have a positive intersection at 0.07 and then 6.9, I'm going to bring that back over here. So we said our intersection is at 0.07, 6.9. We need to be able to decipher that. So we need to know what units we're talking about. So if you recall, in our original parabola equation, in our quadratic equation, our x's represented t's, okay? So our x value in the ordered pair represents time, which in this problem we're measuring in seconds. And then if we look at the name of our equation, y equals was h of x, and that h stood for the height of that football. So what we can say, and that's measured in feet. So what we can say is that, yes, this blocker is going to block the punt after 0.07 seconds at a height of 6.9 feet. Okay, so it didn't take him hardly any time at all to get his hands up in the air and block. So remember, his hands started at 6.6 feet. He just barely had to move any, and he was already blocking that punt. For our second example, it says, in 1980, Susie and Jason received a gift of $1,000 from their aunt. Susie put the $1,000 into the bank. Each year, she added $750 to the account. Jason invested his $1,000 into technology stocks. The value of these stocks climbed according to the parabolic curve until it peaked at $20,600 in 1994. By 2008, the stocks had fallen back to the original value of $1,000. Formulate a function to represent Susie's investment as a function of years and a function to represent Jason's investment as a function of years. So this one's going to be a little bit more tricky because we've got to decipher exactly who is the parabolic curve and who is the linear line. And then we've got to figure out what to do with our years. So anytime we're dealing with years, we always want to make our starting point or our first year, year 0. So we're going to call 1980 x equals 0. Because as we're looking at our coordinate plane, our starting value of $1,000 is going to be our y-intercept. Okay, and that's in 1980 or year 0. So Susie is going to put the exact same amount into her bank every single year. So her rate of change is going to remain constant. So she's going to start at 1,000. She's going to move up to 1,750, 2,500, 3,250. Susie's going to be the straight line. Okay, Jason's going to take this initial investment. It's going to grow till he gets to 20,600, and then it's going to curve down again. It's going to drop off. So for this problem, Susie is going to be our linear function, and Jason is going to be our quadratic. So for Susie's linear, y equals mx plus b. Okay, m is our rate of change, or how much it's changing every year. B is our beginning value. So we know that it's changing by $750 every year, and her beginning value was 1,000. So for Jason, we need to fill out a table of values. So in 1980, X is always going to represent our time. So this is going to be year number 0. So this is going to be our years since 1980. And then Y is going to represent the amount of money he had. So in year 0, he had $1,000, 1980. That's what he got from his aunt that year. Okay, it says he put it in the stock market. In 1994, he had $20,600. So 1994 is 14 years after 1980. So this X value is going to be a 14. And then finally, the last number it gives us is 2008. And in 2008, he was back down to his $1,000. So 2008 is going to be 28 years after 1980. So we're going to take these values right here, X and Y, and we're going to put them into a table in our Desmos. In order to create our table, remember we're going to hit the plus sign and we're going to add a table. So we have year 0, $1,000, year 14, $20,600, and then year 28, he was back down to $1,000. So we've got those 3 values, and I could zoom out and see them as points. I'd have to zoom really, really far though, because we're dealing with 1,000 right there. We're dealing with 20,000, and then, well, actually, both of our 1,000 points are really close together because our Y goes from 0 to 10,000 right there on the screen. Okay, to get our regression, we're going to do Y equals AX squared. Remember our standard form, AX squared plus BX plus C. And I'm going to just type it as is. Okay, and then remember we have to go back. Since our table has X1 and Y1, we've got to add those 1s on all of our X's and Y's. We've got to add that little subscript. So AX1 squared and BX1. And then finally, we've got to change that equal sign to the little approximation symbol because we don't know that our parabola is going to go exactly through all these points. We just want the closest approximation. Okay, and of course, it's really hard to see our parabola because our Y values go from 1,000 to 20,000, but our X's are only 0 to 28. So it's hard to get a good window. But this tells me my A value is -100, my B value is 2,800, and my C value is 1,000. So A is -100, B is 2,800, and C is 1,000. So we can write our equation, Y equals -100 X squared plus 2,800x plus 1,000. We can take these two equations, set them equal to each other using substitution to solve, or we could try to type them into our Desmos and see what happens. So since these values are very large, and we might have to scroll a lot to see the point of intersection on our graph, let's try to set them equal to one another using substitution. So they're both already isolated for y. So I can take this value and plug it into my second equation. 750x plus 1,000 equals negative 100x squared plus 2,800x plus 1,000. So I'm going to go ahead and subtract my 750x and my 1,000. So the left side completely cancels out. Let me get rid of some of this going on down here. On the right side, I've got negative 100x squared plus 2,050x, and then my 1,000s cancel out. So this equals 0. So I'm going to go ahead and factor out a plain x, and I'm left with negative 100x plus 2,050 equals 0. And now each of those factors I'm able to set equal to 0 and solve. Okay, so x equals 0 is one solution because I set this factor equal to 0. Well, we know that they were equal in year 0 because they both started with that initial investment of 1,000. Okay, and then my other solution is negative 100x plus 2,050 equals 0. So negative 100x equals negative 2,050. When I divide by negative 100, I find out that x equals 20.5. So what that means is that their investments are going to be exactly the same at year 20.5. So I could take that value and plug it in up here to either equation really to see how much money they would have at that point. So y equals 750 times 20.5 plus 1,000. 750 times 20.5 plus 1,000. So they should intersect at the point 20.5, 16,375. So rather than scroll all over on this graph trying to find the intersection, I can press the wrench up at the top and I can narrow it down to that specific region. So my x value is 20.5 where I'm expecting it to intersect. So I'm going to say we're going to go from 20 to 25. My x value should fall between those points. And then my y value, they should intersect at 16,375. So I'm going to go from 16,000 to 16,500. Okay, and I see right here, they intersect. So if I tap on that, it is 20.5, 16.375.